record it quick, so in case there's any questions, let's get started. All right, here. All right, so this is a dissociation constant lab. We're going to be to measure a dissociation constant of a weak acid, and that weak acid in particular is going to be acetic acid. So we'll be determining the dissociation constant, or the Ka, of acetic acid in this lab, and we're going to use various methods to do that. So you can test different ways of measuring the Ka. We're going to do the direct method, which is basically measuring the pH of the acid and then titrating it with a strong base. Sodium, in this case, the strong base is going to be sodium hydroxide. The second one, we're going to go through and we're going to generate a full titration curve, and then we're going to use the Henderson-Hasselbalch equation to calculate our Ka. And then the last one is the half neutralization method, right? And this is then going to be used again in conjunction with the Henderson-Hasselbalch equation in order to calculate our Ka. All right, let's look at the first one. So the direct method. So measuring, basically when we're using the direct method, we're going to measure the pH of the acetic acid solution, and that pH of the acetic acid solution is going to give us the concentration of our acid present in solution, right? And then we're going to do a complete titration with a strong base that's going to provide the concentration of the undissociated acetic acid. So what this means here is, right, we have acetic acid and we have an unknown concentration. Well, we're going to react this with a strong base, in this case sodium hydroxide, right? And this is going to react in an irreversible process, right? It's not reversible. We're going to form CH3COO minus plus water. Obviously, the sodium ion is still floating around as a spectator ion in this reaction. And what this is going to be able to tell you is, right, in this first step, is the number of moles, whatever number of moles you have here is going to be equal to the number of moles of sodium hydroxide that you're going to add. And what we're going to be doing here is we're going to be adding an indicator, right? And with that indicator, we'll see a color change at the point in which when we no longer have any acetic acid left, right? So and the reason we can do this, right, is because it's a 1 mole to 1 mole ratio. So we know that whatever quantity in moles that we add of sodium hydroxide is equal to the amount of acetic acid we have. Then we're going to use the equilibrium of acetic acid and water, and then we're going to generate an ice table, and that will allow us to calculate the Ka, right? So we have our acetic acid, right? The typical acid reacts with water to generate the conjugate base and protons. And there's going to be a Ka associated with this, and the Ka associated with this is what we're trying to figure out. And you can see in this reaction, when we first measure that pH up in step 1, right, the pH is going to be able to give us the concentration of protons that are in solution, right? Because the pH is just basically going to be equal, the concentration of protons is equal to 10 to the minus pH, right? Because in any equation, right, pH is just minus log of the proton concentration. So we're able to gather a couple points of data, right? So, and this full titration is going to give us the actual initial concentration of our acetic acid, right? That's in step 2. So we're going to know what the initial concentration of acetic acid is. We know that in the beginning, right, there's 0, just like a traditional ice table. We have 0 concentrations for our acetate and our hydronium ion. And the reason we know this, right, because we're starting with a 0.05 molar solution. And when we're doing a titration, the reason we want to do that is if you take your sodium hydroxide, and we can take the sodium hydroxide pellets and we can weigh them on a scale, and we know, and we get an actual number quantity of the amount of sodium hydroxide we have. So we can then, when we dissolve that in a known volume, we can calculate an actual known concentration of sodium hydroxide, right? So that allows us to work backwards, right? Because we know our known volume, we know how the volume of sodium hydroxide that we add, and from that volume of sodium hydroxide, right, the volume that we add of sodium hydroxide, we know the molarity of the sodium hydroxide because we made it up fresh. That allows us to calculate the number of moles of hydroxide ion that we used in the reaction mixture. And, since the equation that I showed you up at the top here, where we have 1 mole of acetic acid is equal to 1 mole of sodium hydroxide, that's just showing this here. Since we have a 1-to-1 ratio, we can then make the assumption that if we use these number of moles of sodium hydroxide or hydroxide, it's going to be equal to the number of moles of acetic acid that's present in solution. And then we can use those moles of acetic acid divided by the volume of the solution to give us the concentration of the acetic acid that we initially start with, right? So that's how we calculate and are able to calculate this start here. What we do know from step 1, where we measure the pH, is, right, the pH is going to show us that change in hydronium ion concentration, right? So this X that we usually have, right, this plus X, this volume X is going to be coming directly from the pH. So we're able to calculate that just simply by measuring the pH of the solution. We know because of that, we know what the concentration here of the acetate is going to be. And we can then calculate the equilibrium concentration of our acetic acid because we have the change and we have the initial there. So from there, we're just simply going to be plugging all the information into our Ka in order to calculate the Ka of the reaction, right? So it's pretty straightforward because we know what X is because we measured the pH, we know what the initials are, and we have all the data necessary. All the equilibrium concentrations are easily plugged into the Ka equation. So it's a pretty straightforward method. You're going to be given, so if you see the little red bullet on the side here, you're going to be given, and maybe I'll show you a sheet. Let me show you right now, maybe. Let me pull it up. Right. So you're going to be given and it's posted online. I think I turned them on. So you're going to be given a set of data. So you're obviously not able to go through and run through all these reactions, but you're going to have a given set of data of one possibility of what you could have gotten dependent on working through this experiment. And you can see this is basically all the data that you would plug into your tables. And there are 4 different data sets, so we'll basically break it down and just do it similar to last time. We just have 3 different teams worth of data. I guess we'll do, Sean and Katie, you can do, data set 1, Sophia, Jose, data set 2, Helena, I'm not sure if your partner's here, but you have data set 3. Has she joined us yet? No, she has not. It shouldn't be a big deal. I'm going to be online and I can answer any questions along the way. So that's kind of what we'll have there. So you have your data for part A, the data for part B, which we'll discuss in a second, and then there's your data for part C is all here. So and each data set, so each one is titled data set 1, data set 2, data set 3. So you just simply have to use the data set that's posted in Canvas. Get back to here. All right. So that's method 1. the direct method. If we go on to method 2, we're going to generate a full titration curve. Right. So in this case, we're going to plot the pH of a solution versus the volume of sodium hydroxide that we're adding. And we're able to, in this experiment, we were going to, when you calculated during the last experiment, was that when we added sodium hydroxide until we saw a color change in our experiment, right? That color change came about at this point here, right at the equivalence point, right? That's the point at which we have 100% of the sodium hydroxide, where we have, right, the equal number of moles, right? The number of moles of sodium hydroxide is equal to our, right, the number of moles of sodium hydroxide is equal to the number of moles of acetic acid. Right. And that's the equivalence point, because it's at that point, if you think about what happens at this equivalence point, at the equivalence point, as you're leading and getting closer and closer to the reaction mixture, I'm going to go back a slide, right? As we're getting closer and closer, let's just say, for example, if we have exactly 1 mole of solution of acetic acid, when we're at 0.99 moles of sodium hydroxide, we still have protons present, right? There are still going to be protons present in solution. So that those protons will be interacting with the phenolphthalein as a color indicator, and the phenolphthalein will stay clear. Once we get to 1 point, it could be 0.001, moles of sodium hydroxide, right? As soon as we do that, right, we have an excess of 0.001 moles of hydroxide ions floating in solution. Those hydroxide ions now interact with the phenolphthalein and they deprotonate it, and the color change happens. So that's exactly what's going on when you reach the equivalence point. So in this particular example, let's just say you didn't know what the 100% point was, right? So you just simply start adding quantities. So we can try 0%, 20, 40, 60, 80, obviously work our way all the way up to and actually passing by the equivalence point of sodium hydroxide. And we're able to plot that. So you'd end up having little dots on the graph, right? You have little dots on the graph down below, right? And you would get a full, titration curve, and you'd see the color change, and you'd know the exact point at which the color change took place. And right, this is that inflection point, right? This is the inflection point, is essentially what I was talking about here. It's that change, when we change from acidic to basic solution, when we have H+ ions just before we reach that 1-to-1 ratio of hydroxide to acetic acid, and then suddenly we have only hydroxide ions, right? And that's the equivalence point. It's also, an inflection point where the pH changes. All right. So in this particular example, though, right, we can use the Henderson-Hasselbalch equation, right? The Henderson-Hasselbalch equation is listed right here, where we know that the pH is going to be equal to the pKa plus the log of the concentration of the base over the concentration of the acid. And just double check your lab reports depending on when you placed it, when you went through a couple of lab reports early on actually had acid over base accidentally. So hopefully it didn't confuse you when you were working through it. But anyway, so at this half neutralization point, right? So at this point here, we're thinking about the reaction of our acetic acid with the sodium hydroxide. All right, this is the point that we have a 50-50 mixture, right? It's halfway between the equivalence point and 0. And that's, I'm going to use as an example. This is not the concentration we're using in the, in the lab, but if we have 1 mole to start with here, right? This is the point at which we've added 0.5 moles of sodium hydroxide, right? Once we do that, add 0.5 moles of sodium hydroxide, right? If we look at the acetate concentration, right? Initially, we're going to start with, 0 moles here. Let me put the 0.5 on the top. Right. So we're going to add 0.5 moles here. After the chemical reaction occurs, we have 0.5 moles of the acetic acid, we have 0 moles of sodium hydroxide, and we have 0.5 moles of the acetate ion, the conjugate base, right? So this is what happens at the neutralization point, half neutralization point, right? Where now the acetic acid is equal to the acetate. And if we plug this equality into the Henderson-Hasselbalch equation, right? Well, actually, this is supposed to equal 0, so an error here, right? This should be a 0, not 1, so that should be 0. So you take the log of the acetate over, the acetic acid, so the log of 1 equals 0, so this entire right-hand side of the equation goes away. So then, therefore, because of that, your pH is equal to your pKa. So once your pH is equal to pKa, and you can then use that to calculate your Ka, right? Your Ka is just going to be equal to minus your pH at this half equivalence point, right? And the half equivalence point is being pulled directly off the graph. So whatever the pH is here, you're plugging into the equation. All right. So that's the second method, where we're basically, using the half neutralization method. And the third method is also a half neutralization, but this one is using the data from part A, right? So in this example here, we did a full titration, right, where we started, and where it's a little different. It's a half neutralization method, but we had to do a full titration in order to get the data, because you can notice here, we never had a 50% point, right? There was never a point at which we actually had 50%. So when we get the pH, we're pulling the pH off of the graph from their full titration curve. Next one is simply, we know what the 100% point is from part A, right? Full neutralization is, so we know what the 100% point is. So we can, from there, calculate the half of that total volume, right? Because we know what the volume was we needed to get to the full 100%. We just calculate half of that volume of that sodium hydroxide solution. And then we can simply add that volume to a 10 milliliter acetic acid, because we've been using 10 milliliters for all of these. And in this case, we're going to simply mix those two together, measure a pH, and because we're making the same assumption with the Henderson-Hasselbalch equation, that the second half of the equation goes away, right? Because we're still making that pH equals pKa plus the log of A minus over HA, right? So we're still making the assumption that this side of the equation goes away to 0, because it's at the 50% point. We can simply make the assumption that our pH is equal to our pKa, and then calculate our Ka is equal to 10 to the minus pH. So you can see there's 3 different methods that you can do this. Obviously, this one would have required a full titration, full neutralization, followed by 1 extra measurement. And you can see this, the first method had a pH measurement, right? Method 1 was just a pH measurement followed by a titration waiting for a color change. So 2 different measurements. This one required multiple measurements, getting a full titration curve. And the last one was, again, 2 measurements, the full titration followed by a half titration and a pH measurement. So questions? I've been babbling the whole time. Anybody have any questions before we get started? So for the lab, all you're going to be doing is simply, working through. It's hopefully pretty straightforward, I think. I'll be online if you have any questions along the way. Any more questions? If not, then we can just get started. If you want to look at this video again, it takes a little while for me to get it, download it, and then upload it to YouTube and then post on Canvas. But it's on, quickly on Microsoft Stream right after this. So if there are no other questions, you can disconnect and get started.